Hi, Roshan. Welcome to the second part of our
Hi.
webinar on AGI and how to pass the Turing test. Let's continue from where we
Yeah,
stopped.
sure. All right.
Are you able to see my screen?
Yes, I can see. Like we were discussing all the cost function, and then we were
Correct.
moving on that phenotype.
So, oh yeah, I'll give the dice to you. You tell me what have you understood by means of cost function and surprise element and reverse transcription. You could be very frank. If you're not understood, I'll repeat. No problem.
Yeah. So first of all, we have discussed about the entropy and like how we can use the AGI methodologies. I just understood all the basics regarding these whole things and how the phenotype and the cost function it is related. And how we can utilize in a proper way, that basic understanding I have understood. I have got it.
Fine. Okay, now from cost function, that is what we are trying to reduce. And we'll go to the phenotype variation. So I talked about phenotype variation, like the
Okay.
eye color or your muscle tone or things like that. Those are like gene expressions, which could be altered
Yes.
due to environmental factors or through genetic mutations.
Environmental genetics.
So
Yes.
less of genetic mutation, more of environmental factors. So now that gives us an option, that gives us the opportunity to have data augmentation. So what do you mean by data
Okay.
augmentation? Let's say I have your image in front of me. I have the image of Roshan in
Okay.
front of me, and
Okay.
I'll flip the image, a horizontal flip or vertical flip. I flip the image. So what happens? I got another data. So the first image was Roshan 1, and the second image was Roshan 2.
Mhm.
So that is called data
Okay.
augmentation. That is one of the simplest techniques. There are many data augmentation techniques to have data generated. Or you will have to shoot
Okay.
videos of Roshan at different points of time to have different data of your image. Or otherwise, you do such data augmentation practices. So data augmentation is simpler, but you will not have rich variety of data. But with this phenotype variation, we could have the rich variety. So that's the beauty of phenotype variation here. With phenotype variation, we have a rich variety of information for data augmentation, and that will help us for more data generation. And moreover, our reverse transcription ensures that we don't need much data. So even with a single image of Honda CBR, we could detect Suzuki Hayabusa. So we don't need much data. But even if you
Yes.
want more granular data, more data for training, we could use the phenotype variation method. So the training becomes very simple. And then finally, what is the principle in action? These are all the working principle, guiding principle, and primary principle. Now, what are the principles that are going to be helpful for? It will be helpful for a DNA computer. So all this while we are talking about DNA, from DNA to mRNA, then amino acids. So it's all about DNA. So
Yes.
naturally, it will be a DNA computer. So we are talking about computing using biological Turing machine, biological processes. So this will be a DNA computer naturally. And it need not be a physical entity like with the silicon and other stuff. It could be with DNAs. It cannot be even in
Okay.
a enclosure or something. It can be in your body. So my body can act as a computer now. So the DNA is inside my body, and my body can act as a computer, and I
Yes.
could do object detection and stuff. So I'm just trying to, let's say if I have a digital twin, in just say for the namesake, if I have a digital twin, then that will be doing the activity of a biological Turing machine or a DNA computer. So that is the simplest way of forming a DNA computer, but we'll have to think about elaborate ways of creating a DNA computer. So now let's go on to the next slide. I'll go to the slideshow view.
Okay.
Okay, we saw this principles. Now we'll see about the creation of the solution. How do you create the solution out of these principles? So this is going to be a new paradigm in terms of training and deep learning networks used in AI and AGI. We need not worry much about
Okay.
the deep learning networks. So the networks can be modified because the frameworks can exist. The same frameworks can exist but we could rearrange the layering approach and the training approach. With that, we could form a training procedure which is very simpler. So the deep learning framework has some details about the server which you're running, some details about the different hyper tuning parameters, and some information about the pre-trained model which you are going to use, and some parts of customization of the data set, customization of the model, customization of the runtime, customization of hyperparameters, a few other customizations, all these things, and your batch size, a number of epochs, all these parameters together make your deep learning framework. There's not much code in it, in the sense the actual pre-processing and post-processing takes elsewhere. That is the through vision algorithms that takes place elsewhere. So you're not having a exact code of the image processing going on in your deep learning frameworks. Your deep learning frameworks is just for your different layers of your the neural network and how it has to interact with one another, and all these hypertuning parameters and other aspects of your gradient descent based decision making. So the decision making can be based on any method. So we'll take the example of gradient descent. Now, what we have done through our approach is we have made it more efficient than gradient descent for decision making, and also we have avoided the hyperparameter tuning procedure which is required for the normal AI system which we have currently, and it's a lot of effort. Hyperparameter tuning and especially the learning rate adjustments, it's not a very good. It's a kind of trial and error approach. It's not pretty good, and we have less concepts involved. So we have a lot of concepts with the existing training procedure. Now we have less concepts. It's just like transcription, reverse transcription, and some data augmentation. So just two concepts: transcription and data augmentation, and some entropy. So now we could even avoid optimizers and activation functions. I'll talk about what is optimizer and activation functions. When we talk about activation functions, which might use with our translation process, which may or may not, that will help to connect two different DNA computers. So with that, just the transcription process, we could form a DNA computer. And if you add the translation process as well with an activation function, which there are biological activation functions, which have beautiful characteristic curves. So with those activation functions, we could connect different DNA computers. So that will be like your LAN, WAN, and other networks which we have in our current systems using the current protocols and information theory, which uses various physical media. We have the 7-layer of OSI layer network. OSI layer. Yeah, you know that, right?
Yes.
It's called Andhra Pradesh Transport Corporation, something APTSNP. So that's an acronym. So kind of funny. So that will give you all the application, presentation, transport, session, and the data link and the physical. So those 7 layers can be avoided if you have DNA computers which can have activation functions to connect with other DNA computers. So you just need an activation functions to suppress or allow. It's like filtering mechanism. So with a varying range of filtering mechanism, you could have multiple connections. So that's like your IP address or your physical addressing mechanism, and you could have functional addressing mechanism or as well if you have a kind of a bandwidth kind of a thing, kind of a filtering mechanism based on bandwidth, without having a fixed point of filtering. So with that, just by filtering, you could connect to great distances through using a DNA computer. So that's the future of networking. Let's work on that later. But now I'm trying to say we are going to avoid optimizers and activation functions at the a single DNA computer level, and it would work for any characteristic curve. So why do we need activation functions? So we need activation functions to follow a characteristic. For example, ReLU or tanh or sigmoid, all these things are characteristic curves. So you might have heard of what a characteristic curve is. A characteristic curve is like just a behavior which you want your
behavior.
input to. It's like a transfer function with a behavior. So once we have those characteristic curves taken away from the system, it becomes more simpler. So we are avoiding optimizers, activation functions, and through which we are avoiding any characteristic curves as well. So optimizers like Adam and all those different kinds of optimizers, and that is again a kind of a hyperparameter which we'll have to choose, and that's pretty cumbersome. And it's like a not we won't be able to say which is the best choice. So now what is the future expansion? So now we have talked about our current training procedure. We have talked about the principles involved in our formation of AGI system, which would eventually result in a DNA computer. So what is the future expansion, or what is the result of our principles which we are trying to put in action? The first one is going to be Turing test. So with this principle, we are going to pass the Turing test. So once the AGI principles are met and we have constructed a system with these principles in place, we are going to pass the Turing test. That's pretty straightforward. The next one is going to be DNA computers. That's also pretty straightforward because we are already talking about DNAs. We are only talking about DNA, so naturally it has to be a DNA computer with many states. That's the advantage of this DNA computer. There are many phenotype variations. And unlike the binary states, which are just 0 and 1, which has just 2 states, these phenotypes have a lot of variations and you'll have a lot of states. Just like a quantas, different quantum states, you will have a lot of variations. And that will give a tough competition to quantum computers. So, but both of them can act in tandem, quantum computers and DNA computers. And quantum computers is something new. DNA computers has been there for a long time in theory. And we are just trying to implement it. So synergy with Swarm AI. Swarm AI, as I talked in another presentation, it's going to be a collective intelligence with individual Swarm devices. The Swarm device could be a human being, a computer, or any entity. And that entity will have as an individual intelligence-based Swarm device, and you'll have collective intelligence, and you'll have collective Swarm intelligence, and you'll have artificial experts. So let's say you have one expert with all the collective intelligence, and that expert keeps on improving his knowledge, keeps on evolving, and he keeps on increasing his expertise. I'll not say his, let's make it an entity. That entity keeps on increasing the expertise, and it will constantly evolve, and it will reach to the stage where it has understood the theory of everything. It has understood the theory of everything by learning from one domain after the another, and it will also try to prove it. So I'll go to that later. So now it has understood the theory of everything. Now quantum AI. Quantum AI is with the advent of quantum computing, we can create new avenues for AGI and DNA computers. So that will be very exciting. So quantum computers are already there. We have good progress in that. And they are able to reach up to 1,000 qubits, if I'm not wrong. So that's pretty good. And once we have AGI with quantum computers and DNA computers, then generalization would be pretty awesome. And since already we have the quantum computers already, and we're going to bring in DNA computers, then AGI would be very good. And what happens next? So next is theory of everything using not physics. So the other day I was talking about not physics, or I shared a classroom presentation on not physics, which talks about converging all the parallel universes by means of knots. So let's say this is one fabric. I have one fabric knit through a single layer of knot. So if I have different layers of these knitted fabric, there'll be different layers of knots. So those are all interconnected, and you'll have parallel universes. So that is the concept of knot physics, and it is an extension of the rubber sheet geometry. So the rubber sheet geometry is used to describe the space-time continuum and curve, and that is there from the 18th century. And Einstein used it for defining the space-time continuum using the rubber sheet geometry. So now this is an extension. The knot physics is an extension of the rubber sheet geometry. And now the reason why we are using geometric modeling is we are dealing with a non-Euclidean space, and a geometric modeling based approach is the best approach for arriving at a theory of everything. So that's the simplest approach than other methods. So geometric approaches, geometric modeling is good. And now AGI powered by Swarm AI operating on a DNA computer based on quantum computing principles could achieve expertise constantly evolving till we reach the expertise of formulating the theory of everything and also proving it. So we do not only formulate it, and we will also prove it by a means of experiments through these artificial experiments.
Okay.
So I just went very fast in this slide. This is a very slide with a lot of information. This is a slide with a lot of information. So you could slowly digest and ask me questions in this.
Regarding this quantum computing, like, so the quantum computing, it will be having a lot of infrastructure and analysis, as well as like the integration, lot of things required.
Okay, go
And
to a
then
Medium
it will be
article. I'll give you a
integrated
Medium
with
article. You could make a quantum computer at home, and in fact I did that. It's just a Medium article. You know the newsletter from Medium, right? So they publish blogs and
yes.
newsletters. So they provided an article which gave us the concept of making a quantum computer at home.
Okay.
So don't worry about the qubits
I have
and
also
how
heard
many
this.
qubits you're going to solve or something. Don't worry about it. But the concept is
Yes.
there. So you could
Okay.
make a quantum computer at home.
Okay.
So don't worry about the infrastructure. We will understand the logic behind it. Scaling is not a problem. See, bringing to industry scale is what is done by all the organizations and people who have the resources. But for us to understand the concept, you could just scale it down and create a quantum computer with less number of qubits. That's fine.
Okay. Understood.
And what about theory of everything using not physics? So not physics, you're able to understand, grasp what is happening with not physics.
And this phenotype, under DNA computers, so this phenotype, like DNA molecule, they are having, I think, 23 pairs. So all will be interlinked, and
Don't worry about
interconnected
that.
and
No,
shared
no,
with each other.
we are not dealing with the genome map or the genetic map or
Okay.
the chromosomes, or we are not
Okay.
dealing with all those things.
Okay.
We are just dealing with the
All right.
part of the DNA which is involved in the protein synthesis process.
Okay.
So
Understood.
the first one is DNA to mRNA, that is transcription, and mRNA to amino
Transmission.
acids is translation.
Transmission.
This is the only process we are dealing with, and those have some combinations of they also have their own coding. It says it has some pairs, and then it has a stop kind of arrangement, so stop. So it's just like your UART communication or any other communication which has a stop bit, parity bit, and all those things, right? So they have similar stuff for their
Okay.
information coding. And now we are dealing with that, and we are getting phenotype variations because there are transcriptional errors. Transcription errors.
Okay.
So that the phenotype variations can occur due to environmental changes as well. Though we can discuss about that in terms of a behavioral model, in terms of parameters, environment, and stuff. That is different. But if there are errors, and if there are errors which are causing a phenotype variation, that is also good for us. So how many ever variants you have, it means you have different states.
Yes.
The sweet are the uses of adversity. So this is a very apt situation for that saying. Sweet are the uses of adversity. So since we have adverse situation with transcription errors, we are able to build DNA computers.
Okay.
Yeah, that's all. I guess the next slide is our swans, our team all over the world. So we have Anna and I in the AnaVJ insignia. Then we have Anna and Anastasia in Kishnau. And we have Ana Perez in or Cecilia in Portugal. We have Elizabeth, Florida. My mom in Sao Paulo, Brazil. We have Zakaria in Dhaka, Bangladesh. We have Abbas from Hyderabad, Pakistan. We have Roshan from Bangalore, India. And we have Manigandan and his wife from Singapore. He's currently doing his like having his vacation in Malaysia. He's in Singapore.
Okay.
Manigan, he's my college mate. So this is our team. And in fact, I've not added photographs of a few other team members. Once they become active and start getting involved, we'll just add them and we'll make a collage and we'll.
Yes. Nice to have like where all teammates are there, and also it will be good like if whole team will meet together, like what all the Swans, if we are together in any like meeting part or meeting, that will be very good. So we can interact and we can discuss more things. That will be good.
Yeah, so this is the saying of many great scientists, including Robert Feynman. Don't confine yourself. Don't go for a predetermined approach. Think out of the box. Think out of the box is like a term which is used many times and people ignore its significance. So let's not use that term. Let's use a different terms like this phrase which says, don't confine yourselves. Don't confine yourself. Don't have prototype fixation. So if I would have had prototype fixation, then we would never have come up with a different approach for training procedure. We will always think that training procedure should happen in this predetermined format. So we should not confine ourselves and think in a different manner, in a manner which is not constrained by any predetermined approach. So that's it I have for our session on AGI and how we are going to pass the Turing test. We will go build a DNA computer slowly. That's not pretty difficult. You just have to do the protein synthesis. That's your DNA computer. So with a single process of a protein strand or amino acid, that will be your small DNA computer.
Okay.
I don't know how many calculations can do, but it's been calculated by a renowned scientist or physicist in 2003 that you could do 100 teraflops calculations
Okay.
using a DNA computer at that point of time, in 2003. Now it can go to exaflops as exaflop, petaflops. Because the normal supercomputers do at such high rates, exaflops. So DNA computer can be even
Yes.
bigger than exaflops in the current generation. In 2003, it was like in terms of
So
100 teraflops. At that point of time, the fastest
okay.
supercomputer was 32 teraflops, 30 to 52 teraflops. It was NEC supercomputer. That's the Earth simulator. That was the fastest supercomputer then in 2003. And at that point of time, the DNA computer could operate at 100 teraflops.
Okay.
So that's the significance
So
of
it
a
will be a
DNA
very strong computational power,
strong computer.
like
That's because of the
we
number of
can,
variations it has
correct.
in terms of the phenotypes. So that's pretty awesome. This is a very interesting topic. DNA computers are pretty interesting and simple to create compared to quantum computers.
Yes. Just we need to have more advanced details on the protein
Yeah, see, there are a lot of
synthesis and
tools available. There are tools for modeling these transcription
okay.
phenomena and a few other phenomena are taking place at the DNA level. And with these modeling tools, we could create a good machine, good Turing machine. Biological Turing machines are already in place. So if you elaborate that, that will become your DNA computer.
Okay.
So there are Turing machines in every field: biological Turing machine, chemical Turing machine, physical Turing machine, and all those things. A physical Turing machine is nothing but your normal computer. The normal computer which you are using silica is just a physical Turing machine. This is a normal computer. A biological Turing machine is what we discussed so far, and a chemical Turing machine is, let's say,
Okay.
okay, now the recent advent of the click chemistry. The click chemistry, and you just click different molecules and form different blocks. So that will be your chemical Turing machine in a very simple manner.
Okay.
That may not be the exact analogy, but there are chemical Turing machines which have a detailed process. But click chemistry is also an example of a chemical Turing machine. So you will have Turing machine in every field. You can have linguistic Turing machine as well. If you
Okay.
construct a machine using semantics. Semantics means association. So you have words. Like NLP is nothing but a linguistic Turing machine. So you have
Okay.
natural language processing, right?
Yes.
So it associates words properly, and it has a proper grammatic structure. It forms the order properly, and all those things, and it forms a semantic association. That's a linguistic Turing machine. And your knowledge graph is associating information and data into a knowledgeable format and forms a very readable format of information. So that will be your information Turing machine, or you could say data Turing machine, or something like that. And let's say you search your name, or you search AnaVJ in Google. At your right hand corner, you'll get AnaVJ followed by the address and a few other information
Yes.
about AnaVJ. So what is that? That is knowledge graph. That is exactly knowledge graph. You're associating information in a very presentable format. So where does the knowledge graph is being used? So once we have such a beautiful association, it can be used in assistance, voice assistance. It can be used in time sequence analysis, time series analysis, and all those things. These knowledge graphs could be used, and in fact, they're using a gated graph sequence neural networks in a lot of time sequence data and time series information for a lot of stuff. That's pretty exciting. So I was working for GGSSN, rather
Okay.
yeah, GGSNN. Okay, gated graph sequence neural network. I was working for some time, and that's pretty interesting and useful for object detection based on background association. So you have the semantic of a background, and you associate the semantic. Let's say I'm sitting in this room, and the background is the blinders. So the probability is more that I am sitting in front of a blinder than me sitting in front of Niagara Falls.
Okay.
So that is the semantic association. That is the background association, and the knowledge graphs are useful for that as well. Okay, that is a different topic. Let's talk about knowledge graphs and other topics of information mining and data association and other Turing machines in another meeting. So we'll conclude today's session. I hope it's useful for people who are following our webinars. So thank you, Roshan, for joining, and have a wonderful weekend.
Thank you, Vinay. You too have a great weekend, and it was a very good informative session. Really, I got more information and I have enjoyed it. It was very good.
I would know whether my session is informative only if I'm able to convey a concept or explain a concept which is new to the audience, new to the person who's listening. If you already know the associations and the literature and the knowledge of a topic which I'm presenting, then even if my presentation is not on par, it'll appear good. But if you don't know, if you're new to this topic, and if I'm able to explain to you in a good manner, that means my session has been effective and presentation has been good. So I hope it was fine. It was good enough for you to understand
yes.
a new concept.
Correct.
Yeah, I'll feel happy, and I'll go and enjoy my weekend. Just kidding. Okay, so have a wonderful weekend. Thanks, and let's meet on Monday.
Sure. Thanks. Bye-bye.